Hey guys, how we doing?
Hey.
Hi folks, just remember we have an exam. It's on Friday. It'll be in the auditorium, in Pelcha Auditorium. Remember, I'll have a seating chart, just like I've done in the past, although I know I have a couple of new students. There'll be a seating chart in the lobby, so come a few minutes early and find your seat. It's like a week later. Come in early and find your seat. It can be cold in the auditorium, or it can be hot. I don't know, but bring a jacket, dress accordingly. And you have an hour for the test, so it starts at 10:45 and then it'll go till 11:45. So you get 5 minutes extra. My help session tomorrow is at 3 o'clock. Remember, you can get extra credit, 3 points per session if you attend up to probably about 15, I'm not sure. But you can get extra credit by going to the help session. If you can't attend, for whatever reason, just send me an email and I'll send you instructions on how you can get that credit. Okay? That help session is in Beauregard 1, was it 04? I sent a message out. What is it?
101, the auditorium is 101.
No, it's 104. Beauregard.
Yeah, the beginning is 104.
I think it's in the message that I sent you. It'll be tomorrow. I'll record it and put it under help sessions on the website. The exam has 28 questions, multiple choice. Those fall into basically 4 categories, or maybe 5 categories. You have static charges, the properties of static charges. You had some of those on your OpenStax homework assignment, and then also we've seen them in class during class sessions and on your practice homework in the workbook. Forces, Coulomb's law, fields, potential, and potential energy. You'll have both calculations and conceptual questions. The conceptual questions will be similar to what we've had in class. You can find the concept tests. Gosh, we didn't finish the concept tests. They're online. The concept tests, you can download them. We'll go through them. If you have any questions about them, then we can look at those. But they are online. I would download them, and then I'll also post a video that has a solution to those. If there are any that are just standing out that you're concerned about. Okay? What are your questions first before we move on? Do you have any particular questions? Yeah. Yeah, equal potential lines. I sort of wrap that up with fields. All right. We'll look at a question later that's similar to your OpenStax question, and that'll use the equal potential line. By the way, I recorded the session previous to this. If you want to go look at that, that was a help session as well. And we may or may not answer the same question, so you can sort of just skim through it if you want and see what we talked about in that session. I realized that the sound was out a couple of days ago, but I fixed it now, so the sound should be just fine. All right. I want to step through with you on a series of questions. I think that for many of you that you'll say, oh yeah, I know how to do that, but just to make sure, because you're certainly going to see this on the test. So what I'm going to do is I'm going to give you a figure. Hey Sam. I'm going to give you a figure that looks, I don't know, something like this. It'll have 2 charges. Let's just give them some values. Let's say this is 4 nanocoulombs, and this is 4 meters, and this is 3 nanocoulombs, and this is 3 meters. Let's just make this negative, okay? It won't be those numbers. I've just picked those numbers because it makes some of our calculations easy. And I'm going to ask you several things. I'm going to ask you, at this point, A, what is the potential? what is the electric field, I'll ask you what is the force on one of these charges, and I'll ask you what is the potential energy of that collection of charges. These will definitely be on the test, or at least 4 of those questions will be on the test. All right, so first let's ask, what is the field at A? All right, the electric field, the first thing that you do is you draw the electric field vectors. I'll call this Q1, and I'll call this Q2. The electric field due to Q1 is in that direction. The electric field due to Q2 is in that direction. I determine that by taking a positive test charge and putting it there and asking myself the direction, what is the direction, ask myself the question, what is the direction of the force? Attractive for Q2, repulsive for Q1. This will be E2, this will be E1. Next, we calculate E1. That's KQ over R squared. 9 times 10 to the 9th, 4 times 10 to the minus 9, coulombs. Make sure you know your nano is 10 to the minus 9 divided by 4 meters. That cancels, 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 and we're left with 9 newtons per coulomb. Oh, you're right, it should be 4 squared. So it's 9 divided by 4, which is, what, 2.25 newtons per coulomb. Okay? You with me? Now I do E2 as well. E2 is going to be similar. 9 times 10 to the 9th. 3 times 10 to the minus 9 coulombs divided by the distance, which is 3 meters squared. That cancels there. This cancels there. I'm left with 3 newtons per coulomb. And then if I want to know the net electric field, the net electric field is going to be a vector that goes in that direction. The magnitude of it is the square root of 2.25 squared plus 3 squared, whatever that value is. And so that would be one question. What is the electric field at this point A? Notice a couple things that I did. That first I had to determine the direction of the vectors. So I just do that with my imaginary test charge. When I calculated these, I didn't put in the negative sign here. So where I had this 3 nanocoulombs, I don't put in that it's negative. That negative comes about when you're putting here. When you're dealing with your vector quantities, forces and fields, you don't include those signs because the signs are wrapped up when you determine the direction of the vectors. Now, I want to determine the direction as well. The direction will be this angle. And in order to do that, I'll imagine a triangle that has E1 and E2, and then the resultant is right there, and then my angle is right there. And so I say theta is the inverse tan of E1 divided by E2. 2.25 divided by 3. And then whatever that angle is. That would be a second question. What is the magnitude and what is the direction of the electric field at this point in space? It'll just be for 2 forces, but you'll definitely have to do it. So make sure that you can do that before you go into the test. Okay? Yeah, Jordan?
You drew the triangle opposite, so it shouldn't be opposite over adjacent.
Did I do that wrong?
3 over 2.25.
So this is E1, this is 2.25, and this is 3. No, that's right. I've just drawn it out of scale, I think. Maybe it's, yeah.
How do you determine which one is Q1 and
I assigned those. So I said that this is Q1, and so this is P1. It's the electric field due to Q1. All right, I know that was fast, running through that. But y'all need to know how to do that. You should know how to do it now. But if you don't, you definitely need to know how to do this. Okay? You'll definitely have this. So that's how you find the magnitude and the direction. The next thing that I would do is I'd ask you to find what is the potential. So what is the potential at point A equal to? Now this is a little bit easier because it's a scalar quantity. I do the potential at point A is equal to V1 plus V2. The potential due to charge number 1 and the potential due to charge number 2. And so that would be K. I'll write out the numbers. 9 times 10 to the 9th. 4 times 10 to the minus 9 coulombs. That's Q1 divided by 4 meters. 9 times 10 to the 9th. 3 nanocoulombs. But I'm going to put my negative there. This is a scalar quantity, and when I'm dealing with scalar quantities, I don't leave out the negative signs. I include them. Divided by 3 meters. That's 9 minus 9, which is equal to 0 volts. So there is no potential at that point. If you forget about whether or not to include the negatives or not, look at your equation sheet. And on your equation sheet for your forces and your electric field, there's absolute value bars around Q, but they're not there for V. And so that'll clue you in that for these scalar quantities, I don't include those negative signs, but I do include them for the vector. Okay, so you'll have to do that too. For certain, you'll have to do it. I might also ask you, well, I will also ask you, likely, what is the force, let's just say on particle 2. What is the force on particle 2? So going back up here, I want to know what force is acting on Q2. First, that force is going to be attractive because it's a positive and a negative particle. So the force on particle 2 is going to be up and in that direction. Now to calculate the magnitude of that force, it's 9 times 10 to the 9th, 3 times 10 to the minus 9, 4 times 10 to the minus 9, divided by the distance, r squared. Notice I don't put any negative signs here. That's wrapped up in the vector that I drew. And then r, I'll use the Pythagorean theorem to find that. That's equal to 5 meters squared. And then that has a certain magnitude, whatever it is. Now I might also ask you, what is the direction of that force? So what is this angle right here? And that angle is going to be the inverse sine, or inverse tan of 4 over 3. I want to redraw this over here. My vector was up and in this direction. This is my angle. This was 4, 3. So theta is the inverse tan of 4 over 3, which is 53 degrees. Okay, 53 degrees above the negative x-axis. Finally, I could ask you, what is the potential energy? The potential energy is K Q1 Q2 over R. That's that 9 times 10 to the 9th times Q1, which is, well, it was 3 and 4 nanocoulombs. 3 times 10 to the minus 9. Actually, I think that was Q2. And was that negative, the 3? Was it negative? Yeah. So I include the negative here. 4 times 10 to the minus 9 divided by the distance, which is 5 meters. And then that would be the potential energy, whatever that value is in joules. Okay? So you'll certainly see all those problems where you have to calculate the potential, the field, the potential energy, and the electric field due to a collection of charges, of 2 charges in 2 dimensions, which is really only important for the forces in the field. With the scalar quantities, it doesn't matter if they're in 2 or 1 dimension, if you're not dealing with vectors. Okay? I think that most of you can do that. Like most of you could probably go into this and do that and do a passable job on it. But if you're not at that, and the way you tell if you're not at that point is you work through those little tests. And there are sample problems that are similar to these. And just see how you do on them. Work through them without any help at all. With nothing. Just have the equation sheet next to you. And then see how you do on that test. And if you make a 70%, then, do more practice, and then go back and take another test, and see how you do on it. And then you'll make an 80%, and then you make a 90%. And before you know it, you'll be doing them perfectly without any error. Right? Y'all don't look very excited about this exam. Are you excited about it?
No.
Like you're not exuding confidence like you usually do.
No.
I don't like that. It makes me a little bit nervous. It's probably the hardest exam that we have to take.
So are you gonna do obviously the one virtually? So you're gonna have like 1, 2, and 3 are gonna correlate to the same.
Yeah, I gave you one figure, and then I'll ask you that about that one figure. It makes it easier for you, so then you're not, you figure out your triangle and what are the angles, and then it's all the same. And the problems aren't dependent upon one another. Like if you get the electric field wrong, that doesn't mean that you're going to get the potential wrong.
I was gonna say, so as long as you like work it out, you might just get questions better if like one's not really wrong.
Right, yeah. The questions are not interdependent. They don't depend upon one another.
So it's not all multiple choice?
It is almost. That's not what she meant. She meant that if she missed one of that series of questions, would she miss all the questions? Not necessarily. All right, they're independent of one another. Let's look at another question, because I've had several students ask me about it. It's from your OpenStack. And I think it's a good question because it helps us to think about potential and potential difference, which are very related items, or quantities, and energy that particles can feel. You had a problem on OpenStax, which is due tonight, by the way. Isn't that right? Yes, at midnight, or 11:59. You had a problem where it gave you some equal potential lines like this. I forget what the numbers were, but each of these lines corresponded to a certain potential. I think the outer one was like minus 100 volts, and then say 200 volts, and then say 400 volts, or whatever they were. It doesn't really matter. And so these are potential lines. And then it said that you had a proton. That's my proton. It's a positive charge that moves from 400 volts out to 100 volts. I like to think of this like it's rolling downhill. This is like a topographical map. And this is a high point on the map. And this is a low point on the map. And this proton rolls down the hill, gaining kinetic energy as it rolls down the hill. And in fact, protons, if you remember, and you do need to remember this because it comes up, do they move from high to low or from low to high potential? Well, I always like to go back to this cartoon figure. This is high, this is low, high, low, high. Y'all still can't do that, can you? It's not cool. All right. So if I have a positive particle here, it's going to move from high to low potential. If I have a negative particle, it moves from low to high potential. I just know that because the positive particle is going to be attracted to the negative side. The negative particle will be attracted to the positive side. So positive particles will roll downhill. Electrons do the opposite. If the electron comes to this hill, it's going to roll uphill. That'll blow your mind. So electrons roll uphill. But it's just an analogy, right? It's not actually a hill. It's a difference in potential. All right, so our proton's rolling downhill. And then in one of your questions on your OpenStax, it asked, what's the velocity when it gets to the bottom of the hill? Right, we've done this where we say mgh equals 1/2 mv squared. We did that last semester. You're going to do the same thing here, basically. But your mgh isn't going to be mgh because we're not talking about a gravitational potential. We're talking about an electric potential. And so our electric potential is going to be Q times delta V is equal to 1/2 mv squared. Remember that V is energy over charge. And so that's my basic definition of potential. And so if I want to get to energy, I multiply my potential, or in this case, my potential difference between 2 points times the charge. And so that's what we do here. Q delta V is 1/2 mv squared. This gives me the energy that that object contains, or that it gains when it rolls down the hill. Now on your equation sheet, this is listed as potential energy. And if the proton was moved uphill, it would gain potential energy. But as it rolls downhill, it's going to gain a speed. It's going to get kinetic energy. And so that's what you do here with this one. Lastly, remembering that delta V here is not 400, it's not 300, it's what? What is my delta V? 500 volts, because I'm going from 400 to negative 100. Actually, it's negative 500, but for our sake, we're not really worried about the direction or the sign of it, so we'll just say that it's positive 500. So this is going to be 500. This is Q for a proton, so it's 1.6 times 10 to the minus 19 equals 1/2 m. You know what that is for a proton, times v squared. And I'll leave you to do the rest of that. You had a question on your OpenStax that was very similar to that. It had a figure with the circles on it, and that's how you go about that problem. But it's also a good problem as we're moving into electrical circuits, where we'll talk about potential difference, about how we accelerate these electrons to these speeds as they move into circuits. By the way, I know that this first couple of chapters, they're probably the hardest chapters in this entire 2-semester sequence. Fields, forces, and potential are just difficult topics. They're kind of abstract. It's hard to really wrap your mind around what they are, and they're all a little bit similar, which makes them difficult to keep apart in your mind. But the good news is that though we'll continue using voltages and fields, that we won't use them in the same way that we've seen them here. That this is really an underpinning as we move into circuits. Okay? You'll see potentials and fields a little bit, but not in the same way that you're seeing them here. Okay? Does that make you feel better? You look happy now. All right. What are some questions that you would like to look at? Those are just some things that I wanted to get off my chest. What are some things that you want to get off yours? Yeah, Kristen?
It was from an old exam.
All right. Which one?
Exam 1, spring 16.
All right, this is in the back of your workbook.
Number 6.
Number 6. Oh, yeah.
I kind of get it, but I kind of don't.
All right, let's get it. So here I have forces on this. Number 6, you say? I'm told that cube number 3 is positively charged. So that means to get the vector, that force vector that I have to have a force vector that's up and in this direction, and a vector that's in that direction, right? Like this resultant is the result of adding these two vectors. It's not going to be a vector in this direction and this direction. You can't get that. It has to be these two vectors that give me this vector. You follow? Follow me? So now, what charges on these two cubes, if this one's positive, will give these two vectors to be in that direction? What does this one have to be?
Positive.
It has to be positive. And this one, positive too.
So what would happen if 2 was negative
If 2 was negative,
and 1 was positive?
if 2 was negative, well, 1 would still be the same. This one would be in this direction, and so the resultant vector would be something like this. Okay? Good question. You'll encounter those types of questions, maybe not one exactly like that, but where I give you a configuration of charges and ask you to figure out what is the net force on those charges, or what is the net electric field. Okay? I would expect questions like that, or maybe one like this. This is a good question too. What else? Yeah.
Can you explain number 1 for me?
Oh, the quark one? Was that the quark? Yeah, it seems complicated because we haven't talked about quarks, right? But it's really, all you got to know on this is what a neutron is. What is the charge on a neutron? It's neutral, right? That's what you call a neutron. So it has 0 charge. But a neutron is made up of these individual particles. It's made up of 3 of either up or down quarks. This one is plus 2/3 of the charge, and this is minus 1/3. And so what combination of those will give you 0 charge? Well, if I have one of these, how many of these do I have to have? I have to have 2. 2/3 minus 1/3 minus 1/3. up, up, down gives me a neutron. Yeah. Up, up, down. Yes, you're right. Up, down, down. B is the right answer. Okay? Who asked? Alan, is that okay? You understand? Good. What else? On this exam? All right. We can skim through some of those others. I know that y'all have this one on the back of your in the back of your book, but we'll skim through some of the others too. But you know what? The exams, they're covering the same material, and they're going to be similar. Oh, yeah. So this comes up in the concept test, which, as I said, is online. And I'll send you the video out for that so you can skim through it. I think if you just go through the slides, most of them you'll be okay with. And here, we have a collection of charges. And I want to know, where is the potential equal to 0? Let's first just imagine, let's just sort of get rid of those charges, not think about those. If I have a point right here, and I want to know if the potential is equal to 0. We've had questions like this where I just have 4 charges on a square. Is the potential at that point equal to 0? Well, I ask myself the question, are these 2 charges equidistant and opposite? They are opposite. Are they equidistant to point B? They are. So the potentials of those charges cancel out. And then I ask myself the same question for these 2 charges. Is that true? Yeah, the potentials cancel out. So the potential at point B due to those 4 charges is equal to 0. And then I go and ask myself the same question at point A. Potential is equal to 0 due to those 2 charges and to those 2 charges. All right, so A and B both have 0 potential due to those 4 charges. Now, let's add in these last charges. At point B, the potential due to these 2 charges, they're equidistant from point B, 0 potential. They cancel out. The potentials cancel out. And then at A, do the potentials of those plus and minus 3, do they cancel out? They do, because they're equidistant. Okay. Now, imagine, what if I switched these 2? Like I put this one here and this one here. Then the potentials wouldn't cancel out anymore, because they wouldn't be equidistant from those points in space. It's a good question. You'll probably have something similar to this on the test, just as a heads up. So it's similar to the one that we did with the 4 charges on a square, but you're just adding more charges to it. So what is the answer, by the way? E. E is the right answer. All points along that axis have a 0 potential. Not just A through B, but actually every point along this axis, there is 0 potential. All right? Good question. Let's just take a second. We'll go through that that last concept test. I'm sorry, I just forgot to go through all of it. As I said, it's online. This is like what we just did. Where is the potential equal to 0? We did a question very similar to this. Which points have the same potential, C and E, because they're on an equal potential line? We did one like that in the workbook. I don't know if y'all remember, but we did one. It was a quick test. You're not going to encounter these types of problems. So you can just, if in your workbook, if you just want to cancel them out, I'm just telling you that because we didn't really cover this in class. We didn't go over those questions. But those last 2 questions, you can just cross out. And I'll send you a message. Again, I'm sorry for not doing that. I guess I can just give you all 72 on the exam. No! Huh? No, you're not. No, you're not.
That would be fun.
No. No. No.
You just guarantee that it'll get it.
No. And are you taking it? Yeah, I was telling you what's great. Just email me. I'll see how it's all All right, let's sort of skim through some of those tests. We didn't really miss that much on the concept tests, I don't think. Yeah, I think we got up to this point. Yeah. Look through them, though, because you'll probably have some questions that are similar to these, where I'm asking you, where is the potential 0? And you just want to ask yourself, well, how do the charges, the potential due to the charges, cancel out based on their orientations? Let's see, this is spring 16. Any of these stand out to you I want to look at? I really worked through these old tests. Yeah, Taylor?
Okay, so I understand I can remember 7, but going from 7 to 8, I can work that out.
Yeah. Oh, okay. So this looks like a complicated problem because it's got lots of charges involved, but it's actually not complicated at all. Because if you recognize that these two minus 10 nanocoulomb charges are equidistant from the plus 2 nanocoulomb charge, look, I'm just going to draw the vectors. I have one vector that's in this direction and one force vector that's in that direction. And then I have a third force vector that's down and in that direction due to the plus 5 nanocoulomb charge. But notice that these are the same distances and the same charges. So these two vectors are equal but opposite. So I can get rid of them. And so I'm really only dealing with this vector. All right? So if I want to know I'm going to get rid of those. If I want to know the force, it's going to be K times 5 times 10 to the minus 9 times 2 times 10 to the minus 9 divided by the distance, which is 3 squared. That's how I find the force, which is going to be 10 times 10 to the minus 9, or C. And then if I want to know the direction, well, what is the direction? You know what the answer is? D, right. It's not off of any axis. It's just straight down along the negative y-axis. So D is the right answer. So let's look at another problem, because I don't think that's really what you're getting at. Let's look at a different problem that'll be similar, where I'm asking for the direction. Like this one right here, where here I'm not asking for a force, but I'm asking for the direction of the electric field. We worked one similar to this, but you'll definitely have it on the test come Friday. Here, I want to draw my vectors. I have one in this direction and one in this direction. And then I would calculate what are the magnitudes of those electric fields. I'll call this E1, I'll call this one E2. And now I want to know what is the direction of the resultant vector, say this angle theta. In order to find that angle theta for the next problem down, I would say that theta is the inverse tan of E2 over E1. This is just like the problem we did earlier at the beginning, where I had these two charges, and I have to find the magnitudes of these vectors, and then using KQ over R squared. And then I have to find the angle of the resultant vector. So this is a triangle. I shift this vector over to here. I'll draw that. Because I can do that to vectors. I can move them around however I want, as long as I keep their direction and magnitude the same. And then I got this triangle right there. I can find that angle theta using my tan function. Taylor? Okay. What else, folks? Sally?
Number 3 for exam in 2003.
Oh, yeah. You actually have a homework in the workbook. I know that many of y'all don't work those problems, but they're actually fairly useful for you to go through. They're good practice for the exam. Remember, F is equal to QE. And so what I have here is a charged sphere that has two forces acting upon it. It has the force weight of it, and then it also has the electric force. And what you're doing here is you're setting the electric force equal to the weight. Now the electric field, it tells me, is pointed downward. So if the electric field is pointed downward and the electric force is pointed upward, what is the sign of the charge? Is the charge positive or is it negative? Well, I know that the electric field is in this, like if I imagine my imaginary positive test charge, it feels a force, and the force is in the same direction as the electric field. So in this case, what is the sign of the charge? Is it positive or is it negative? It's going to be negative because negative charges feel a force that's opposite the electric field. It's just the opposite of what we said before. All right, so this has to be a negative charge, so it's either A or B. And the way you find it is you say, well, FE is equal to FW. QE is equal to mg. And then you solve for Q, mg over E. All right? And then whatever that is, I forget what the answer is. Do y'all know? It's A. So that works out to be 0.012. It's going to be 1.2 kilograms times 9.8 divided by 1,000. All right, I think I used 10 here for G. Yes, that'd be negative 0.012. Yeah, that's right. Okay. Allie, that's a good question. I know that we haven't seen one like that, and you probably wouldn't see one exactly like that, but you do need to know how electric fields work. You definitely need to know how to determine the force of an electric field, and then also what is the direction of that force on a positive or negative particle. So that way,
Are we gonna have types of questions like that that give us a downward or upward direction, so we have to look at that?
yeah, maybe. Yeah, that's something I want to do. I want you to do that. Yeah.
Okay, so kind of like we'll all do the same thing with the field and everything. Number 15 on 2014. I didn't really understand how you got upwards or downwards. Like I got the number on it, but not how you figure out what direction it was in.
Oh yeah, this is a similar problem. Well, same, it's a very similar thing. So my FE is up, my FW is down, but here I tell you that it is a negative particle. That means that if FE is up, E is down. That negative particles feel a force opposite the electric field. Just like positive particles feel a force in the same direction as the electric field. For negative particles, it's just the opposite. And so here, the electric field, since the electric force has to be up, because it's opposite the gravitational force, that's your first step. My electric force has to be here because my weight force is in this direction. Then you say, oh, but it's negative, so the electric field has to be downward. It's basically the same question, just a different thing missing, different piece of information. Is that clear? The electric field, right. Which is nothing new, because we've said that positive charges feel a force in the same direction as the electric field. So negative charges just feel the opposite of what positives do. They always do the opposite, because they're negative. All right, what else? These are all good questions. Sort of skimming through. If you see anything, let me know. You won't see one like 21 here. This is spring 14. Make sure you know your units for potential and forces and fields. Remember, potential is energy per charge, so that's joules per coulomb. Fields are forces per charge, so that's newtons per coulomb. What else, folks?
This is where like I usually just, I try to skip over the units.
Yeah.
And that's like the thing that cancel out and stuff, so it's asking the electric differential. But volts wouldn't be electric.
Yeah, volts are electric potential. I mean, that's our basic unit for. That's what we use for potential is volts. Huh? No, that's electric fields are newtons over coulombs. So volts, yeah. And, you know, if you get one of those and you're not certain, look at some of the other problems, because I'll certainly give you potentials in the other problems and look for those units. Let's just sort of write down the units. So for fields, the units are newtons per coulomb, and by the way, that is kilogram meter per second squared coulomb. Right, that's MA, mass times acceleration, divided by my charge. I can also have this, and we saw this, as volts per meter. So a field is also a volt per meter. For potential, that's a volt, which is, potential is energy per charge, so it's joule per coulomb. And then if I want to express it in my most basic SI units, well, let's see, a joule, I always think back to kinetic energy. That's kilogram m squared over second squared. That's mass times velocity squared divided by coulombs. Just go back to your equations and think about what those are. The equations that you could potentially need but not have on your equation sheet, there are really only a couple. Like your kinematics equations, x is 1/2 at squared, v is equal to at. I think y'all know those. And then the kinetic energy for mechanical kinetic energy is 1/2 mv squared. Like in the problems that we worked at the beginning. I think y'all know those, so I think we use them a lot.
When you think you use the x equals
Oh, if I give you a problem where I ask you what is the velocity or the position of a charge after so many seconds in an electric field, let's see if there's one on this exam. I'm pretty sure there's one on the S16 exam. Yeah, like number 15 right here. This is spring 16, like in the back of your workbook. On this one, you would first have to find the force. The force is QE. Then you have to find the acceleration. That's F over m. And then in this case, I'm looking for velocity. So I would find the velocity as A times t. We did one of these early on, but you'd have to go through that step, those three steps. If I'm asking for the position, then it would be the 1/2 at squared. All right? Anything else?
Chapter says which equation sheet are we using?
You get the one in the back. Yeah, I'll print it out. It'll be on the back of your form. So, no, I'll give you a form. You'll follow that. You use the form. The form. Yeah. Well, I'll send out a message on how to use those. I think most of you know how to use those. Alrighty? I need to send you a message about the concept test, just to remind you to look at those and to remind you that we're not going to do those last few questions. I'll send you a message about that for a video on that. But I'm wrong. Well, the good news is that once we get past this chapter, that we sort of move away from the first semester stuff. We're not doing vectors again. We get into circuits, and circuits are a lot of fun, actually. They're like a little puzzle that you have to put together. And when you write, and light's pretty simple, too. It's just some simple rules. And then when we sound, the sounds some kind of cool. Okay? Anything else, Bill? Maybe proud on Friday. I want everybody to do well. Y'all have a good day. See you.